So we completed 2 modules of this course. First is divide and conquer and second is greedy algorithms. Now we start today third module, dynamic programming. So first we review the algorithm design techniques. First was divide and conquer, and in divide and conquer we divide our large problem into smaller subproblem, solve the subproblems and combine them to get the solution. So the first characteristics of the problems for which we design divide and conquer algorithms is that they should have disjoint subproblems. So we just quickly review divide and conquer. So we should have disjoint subproblems. By disjoint we mean the problems are distinct. We have to solve both, whatever number of subproblems are there. So just for a review, first was defective chessboard. Defective chessboard problem, and here we have 4 subproblems, and all are disjoint, means we get 4 distinct subproblems, we have to solve each. Next was Karatsuba's multiplication algorithm, integer multiplication algorithm. Here we have 3 subproblems, and again the smaller subproblems are distinct, we have to solve each. Next was matrix multiplication, Strazen's algorithm, Strazen's matrix multiplication algorithm, and here we have 7 subproblems and all are distinct. Then we studied Gaussian elimination. And here we have only a single subproblem, and it is smaller subproblem and obviously it will be distinct. Finally we studied fast Fourier transform, in short FFT, and here we get 2 subproblems, even and odd problems, again they are distinct. So next, this is divide and conquer. Next module we studied was greedy algorithms. So just I will review characteristics of greedy algorithms. They have 3 characteristics. First is, so a single subproblem we get, single subproblem. Second is greedy choice property. Greedy choice property. So greedy choice property means local optimum implies global optimum. So this is local optimum implies global optimal. And third is incrementally build the solution. Incrementally build the solution. These are 3 characteristics, and some example problems that we studied was, so first was fractional knapsack problem. Second was Huffman encoding. And third, interval scheduling. and finally it was optimal caching. Optimal caching. So today we will study dynamic programming. Optimal caching. So today we study dynamic programming. So for dynamic programming, the problem should have overlapping subproblems. This is the requirement. Here we should have overlapping subproblems. So just for comparison, in divide and conquer we should have disjoint subproblems. For dynamic programming we should have overlapping subproblems. So what we do in dynamic programming, we solve the subproblems only once and reuse the solution to save our time complexity. So the simplest example that I can give is computing Fibonacci numbers. So first example we'll consider to explain dynamic programming and about overlapping subproblem. Computing Fibonacci numbers. So you must be knowing Fibonacci numbers. We start with f0 equal to 1, f1 is equal to 1, and for n at least 2 we have a recursion. Fn is equal to sum of previous two Fibonacci numbers, fn minus 1 plus fn minus 2. So this is the recurrence. So here you can see solution to original problem depends on two subproblems, the previous two, fn minus 1 and fn minus 2. So here we can easily observe that computing fn requires smaller fn's multiple times. You can easily see if we make a recursion tree. So just to give an example, suppose we want to compute f5. So recursion tree, how it makes, suppose so I will not write the function recursive algorithm for computing Fibonacci numbers. You can easily write it. So just assume that this fib n is the recursive algorithm. Algorithm for computing fn. So just assume this. So we use this recurrence. So basis of the recurrence is for 0 and 1 directly answer 1, for n at least 2. So this fib n will call fib n minus 1 and fib n minus 2. So this is the these are two recursive calls we have, and basis is 0 and 1. For 0 and 1 there is no recursive call, we directly return the answer. So now just make a recursion tree for computing f5. So we can easily make recursion tree for computing fib5. So original call is fib5 and it has several recursive calls. Fib5 is the original call. So it will call fib4 and fib3. Then fib4 will call 3 and 2. Fib3 and so here it is not showing properly. So just use your imagination, and 3 will call 2 and 1. Fib 2 and Fib 1. So this 2 also 1 and 0 it will call Fib 1 and Fib 0. Similarly for this 2 also 1 and 0, Fib 1 and Fib 0. 3, this 3 will call 2 and 1, Fib 2 and Fib 1, and finally this 2 will also call 1 and 0, Fib 1 and Fib 0. So this is complete recursion tree. We start with Fib 5, continue up to the basis. So now you can easily observe. Yes.
So why is there a need to call Fib 0 and Fib 1 on the right hand side of the tree? I mean, if you are using dynamic programming.
I am not using dynamic programming. I am using just simple recursion. Just wait. So here my objective is to show that we have several subproblems. If we solve it simply using recursion, using this idea. So you can easily observe that several times these are called, and we can count. So we can write Fib 0, how many times it is called? We can count actually 1, 2, 3. It is called 3 times. Fib 1, this is called 1, 2, 3, 4, 5 times. Then we have Fib 2. Fib 2, here we count 1, 2, 3 times it is called. 3 times, then we have 2, 3. Fib 3 is called twice. So we can easily see we have several overlapping subproblems, mean same subproblems are called multiple times. So this increases our time complexity. So first we compute time complexity of this simple recursive algorithm, and it is easy to compute. We will see that it is exponential time complexity. So we start with computing its time complexity. Let Tn be the time complexity for computing Fn using the algorithm Fibn. So you can easily write the recursion. So Fibn will call Fibn minus 1 and Fibn minus 2. Fibn minus 1 will take time Tn minus 1. Fibn minus 2 will take time Tn minus 2. Once you get the answer, you have to perform one addition. So assuming that addition takes constant time, so we get our recurrence as Tn is equal to Tn minus 1 plus Tn minus 2 plus 1 for n at least 2, and for n equal to 1, for n equal to 1 or 0, we can take Tn as some constant. So we have to solve this recurrence. There is no need to solve this exactly, it will become complicated. I will just show a very simple method to get asymptotic notation. So just observe that this we can write. So this recurrence we can write Tn is greater than tn minus 1 plus tn minus 2. This we get. And we can solve this. So what we do is, first we solve, suppose if we have t prime n is equal to t prime n minus 1 plus t prime n minus 2, we solve it. So that is exactly like we can say Fibonacci series. So, and there is a very simple formula for Fibonacci series. So for solving this, we get something like, if we take this t prime n is equal to t prime n minus 1 plus t prime n minus 2, and using the same boundary conditions as in Fibonacci series, assuming that for simplicity, otherwise also you can prove similar results. So we get this t prime n simply as fn, and we have a very simple formula for fn. Exact formula you can compute, but in asymptotic notation it is big theta of square root of 5 plus 1 divided by 2 to the power n. So this Tn will be larger than this. So we can write in asymptotic notation, Tn we can write is equal to big omega of square root of 5 plus 1 divided by 2 to the power n. So we get exponential time complexity. This is because our subproblems are getting repeated. So in dynamic programming, what we do is avoid repetition. So there are basically two techniques for dynamic programming. First, top-down approach using memoization. Second is bottom-up approach. So both I will describe. So first method is top-down approach using memoization. So here what we do is we use the same recursive calls, but the difference is yes, this is dynamic programming. So just this is dynamic programming approach. So we use the same recursion method, but the difference is, first time when we compute a function, when we evaluate first time any subproblem, we store it in a global array and later reuse it. This is the idea, to avoid solving the same subproblem multiple times. So once again I will show the recursion tree and using the global array. So same example we take. So call this new function fib2 n. So fib2n, what it does, it is same recursive algorithm but using global array. First time whenever we evaluate any value, we stored it in global array, and next time when it is referred, we simply look into the array and avoid the corresponding subtree. So assume this algorithm. I will not write the code, you can simply easily write it. So just making recursion tree with global array for fib25 for computing F5. So fib25. Now recursion tree is very simple. So first it will call fib24. It needs also fib23. So first continue with in depth first order fib24. Again it will call fib23, and also it needs fib22. So once again go down the recursion, continue like this, fib22, and this also needs 1 and 0. 3 needs 1 also, it will be computed later. Continue with the recursion. Now we have basis fib1, fib21 and fib20. So these are the basis. There is no further recursion. So what we do is, we know their values. So we make a global array like this. Global array for n equal to, this is n, this is fn, 0, 1, 2, 3, 4 and 5. So first time we get the solution, we store and later simply reuse. So first time when fib1 is called, we store its value here 1. When fib0 is called, we store its value here 1. Now fib2, we compute 1 plus 1 is 2, just store it here in the array 2. Move up the recursion. Now fib3. So fib3 needs fib1 also. Instead of making a recursive call, it will just see this array, global array, and compute 1, just add 1, get the value 3 here. So we know the value of fib3. Again going up the recursion. Fib4 requires, fib3 is already there, fib2 it is also there. So fib2 just see from the array and just add, get the value 5, move up the recursion. 5 requires 3 also. Now both 3 and 4 are in the global array, add. So now you can see structure of this recursion tree. It is simply linear. We call only once. So now the time complexity you can easily compute linear. You can add big O of n. So this is top-down approach using memoization. So by memoization we mean using global array and consulting it whenever we require. So this is less frequently used in dynamic programming. More frequently used is the reverse, bottom-up approach without using recursion. So next is bottom-up approach in dynamic programming. This is most preferred method, bottom-up method in dynamic programming. So here what we do is, so top-down approach, we start with the original problem, break it into subproblems, and whenever we get a solution to the subproblem, we store in global array, and whenever solution to a subproblem is required, we consult the global array. Now bottom-up approach is just opposite. Start with the smallest subproblems and move up to the original problem. This is very simple approach. So again, once again I will show this. So here start with the smallest subproblem. So smallest subproblem is, we know f0 is 1, f1 is 1. So in dynamic programming, again we make array, we make a table. So same table that we have seen earlier, but using bottom-up approach. This is n, 0, 1, 2, 3, 4, 5, and this is fn. Starting with smallest subproblem, 1, 1 we get. Now we compute f2. It is sum of previous two values. This is very simple. Just continue like this. f3 sum of previous two values, 3. f4 sum of previous two values, 5. f5 sum of two previous values, 8. Again time complexity is same, big O of n. So this is bottom-up approach, and this is most preferred method in dynamic programming. So we make a table and fill the table starting from the smallest subproblem. So this is a very simple example. Next we take 0-1 knapsack problem. So fractional knapsack problem we have considered earlier in greedy algorithm. So fractional knapsack, we can take a fraction of an item. So in 0-1 knapsack, this is not allowed. So now the example problem we choose is 0-1 knapsack problem. So by this 0-1 means either do not take or take. Do not take or take an item entirely. An item entirely. So either we take an item or we do not take. So this is 0-1. 0 means we are not taking, 1 means we are taking. No fractions are allowed. So this is a variant of the original fractional knapsack problem. So fractional knapsack problem we solved using a very simple greedy algorithm. Simply sort the items based on most valuable and start choosing the items in this order of profit per weight, decreasing order of profit per weight. So we'll see that this greedy algorithm will not work for 0-1 knapsack problem. We'll take a very simple example and see that it is not giving optimal solution. Then we design a dynamic programming algorithm, a very simple algorithm. So once again we review this problem. So here we have n items, I1 up to In, in general I, and these are items. Then we have weights. Weights are W1 up to Wi up to Wn, and we also have profits. Profits are P1 and so on, Pi up to Pn. And also we are given a knapsack capacity, capital W. Knapsack capacity, call it capital W. So now the problem is very similar. We have to select items that fit in the knapsack having capacity capital W such that profit is maximized. So once again we can write a formulation. So earlier we wrote linear programming formulation. Now we write integer linear programming formulation, ILP, and this will be used later in approximation algorithms also. So we make integer linear programming, in short ILP, integer linear programming, in short ILP formulation. For this problem 0-1 knapsack. So formulation is very simple, almost same. The only difference is that now the variables can take only binary values, 0 or 1. So it is almost same. I will write it. Our objective is to maximize the profit. So we introduce variables. X1 up to Xn. Each variable can take binary value, either 0 or 1. 0 means the corresponding item we are not taking. 1 means we are taking the item. So if we follow this convention, then profit we can write. We have to maximize the profit. So we write our ILP as maximize sum of all I is equal to 1 to n Pi xi subject to some constraints, and the constraints are items should fit in the knapsack. So sum of all I is equal to 1 to n Wi xi is at most capital W. This is one constraint, and other are for the variables. So each variable can take only binary value, 0 or 1. This is for all I in 1 to n. So this is ILP formulation, maximize sum of all Pi xi subject to sum of all Wi xi is at most capital W, and each xi is binary, 0 or 1. This is ILP formulation. Now a very simple example we'll take and show that the greedy algorithm fails to find the optimal solution, so that we can try dynamic programming. So a very simple example we are considering with 3 items, I1, I2, I3. 3 items having weights Wi 322 and profits are 744, and knapsack capacity capital W is 4. So now first we try our greedy algorithm. So greedy algorithm says choose the item which is most profitable with largest value of profit per weight. So profit per weight, we divide Pi by Wi. For first item, it is 7 by 3. Items number 2 and 3, 4 by 2 each. So each is having value 2. 2 profit per weight. Here it is 7/3. It is greater than 2. So most profitable item is first item. So take it. Its weight is 3. It fits in the knapsack, gives profit 7. But you can easily see this is not the optimal solution. The optimal solution will be choose items 2 and 3. Having weights 2 each, combined weight is 4. They fit in the knapsack. Total profit is 4 plus 4 is 8. So the optimal solution is we have to use I2 and I3 in the knapsack. So the greedy algorithm fails. So now we should design dynamic programming algorithm to solve this problem. So for dynamic programming, first we use some notation, and then so again this is very similar to dynamic divide and conquer approach, that original problem depends upon solution to original problem depends on solution to sub problems. The only difference is divide and conquer we have disjoint sub problems, we have to solve each problem separately. In dynamic programming we have overlapping sub problems. So we save our effort by solving only once the sub problems. This is the only difference. So first we formulate our original problem and how it depends upon solution to sub problems. Then we solve the sub problems bottom up manner. So we use the notation opt IW. So start with let opt IW. We make a function. So this denotes the equal to value of optimal solution. Optimal solution using so sub problem how we denote. So there are two elements in the sub problem, I and W. So I means how many items we have to take starting from the first item, and W is the knapsack capacity. So this is sub problem which denotes value of the optimal solution using first I items. So the items are I1 up to II. Only first I items we have to use, and knapsack capacity So just for distinction, this is small w. This is distinct from the original capital W, small w. So this is our sub problem. So the original problem we have to compute opt n with capital W. So now we'll see that this depends on smaller sub problems with smaller values of I and this small w. So how it is done? So first consider the last item. So again for simplicity, consider the original problem, then we'll generalize this to any general solution. So just consider this original problem opt n capital W. So now just focus on the last item in. Focus on last element in. So now there are only two possibilities. The possibilities are that call this O. Let O be the optimal solution. Optimal solution. By optimal solution we mean set of items. So O is a set of items which represent the optimal solution. So now we can have only two possibilities. If we consider nth item, either it belongs to the optimal solution or does not belong. There are only two possibilities. So we consider each separately and see how the original problem depends upon smaller sub problem. So two possibilities we consider. First we consider if the nth item is not in the optimal set, then what will happen? We have to compute opt n capital W is equal to. So nth item is not there. So we have to use item 1 up to n minus 1. Knapsack capacity also remains the same, capital W. So then in this case it is same as opt of n minus 1 with same capital W. Now second possibility we consider. Second possibility is this nth item is in the optimal set. Then we write the equation opt of n with capital W is equal to, so nth item is already there, so it will give the profit Pn. It will give the profit Pn plus, now what is the sub problem? So sub problem we have to use first n minus 1 items. Now the remaining weight of the knapsack capacity decreases. How much? This capital W minus Wn. So again for the remaining sub problem we have to find optimal solution. Otherwise we can make the solution sub problem optimal and further increase our solution. So solution to the sub problem should be optimal. So we get this two possibilities. If nth item is the item, opt n W is same as opt n minus 1 W. If when nth item is not in the optimal solution, when nth item is in the solution, optimal solution, we get opt n W is equal to Pn plus opt n minus 1 W minus W1. So here we get the idea, and using the same we can write for general I. Same idea we apply. Now we write for general I. For a general I, so first we check if this W is Wi, then W is Wi means ith item is not fitting in the knapsack. So we have only one possibility, we have to exclude it. Then opt of IW will be is equal to opt of I minus 1 W. Otherwise, so if ith item is not fitting, we do not have any choice. Otherwise what we do is, so same idea, we have two possibilities. Which possibility we should select? The better one. So we take the maximum of the two. So the maximum of the two we write. Otherwise our equation becomes opt of IW is maximum of the two possibilities. Max of opt I minus 1 W. This is first possibility when ith item is not in the optimal solution. Otherwise add the profit Pi plus, for the sub problem, I minus 1 W minus Wi. So this is the recursion we get. Now same problem that we have seen earlier, we will solve this. So we make a table. Same problem we have, the original problem, just make a table, table of values we make. Having 1, 2, value of I will be from 0 to 3, 4. Zero to 7, 0 to 6, 1, 0, 1, 2, 3, 4, 5 and 6. 0, 1, 2, 3, 4, 5, 6. and 0 1 2 3, 0 1 2 2 3. So these are I values and these are W values. So the problem that we are taking is this. We have 3 items, I1, I2, I3, having weights Wi 2 2 3, profits are 4 4 6. This is different problem. Knapsack capacity is 6. So 3 items for I equal to 0 to 3 we make, and knapsack capacity is 6. So 0 to 6 we make. Now first row, bottom row we see corresponds to I equal to 0. I equal to 0 means we are not taking any item. So the profit is 0. We start with the value 0. Now I equal to 1, we consider first item. So first item we consider, its weight is 2. So this represents opt 1 0. So 0 means 0 is the knapsack capacity. If the item is not fitting in the knapsack capacity, then we do not have any choice. We simply copy it directly like this. Here it is written. If the considered item is not fitting in the knapsack, then opt IW is opt I minus 1W. So this means just below the row. So we simply copy. Just copy this. So we get this value 0 here. Here also copy. Now this value, we have 2 possibilities. The 2 possibilities are the item, we choose the item or we do not choose the item. If we do not choose the item, then simply copy this. So we have to consider two subproblems, one directly below it and one below it less than the weight. So 2 minus the current weight of the ith item, 2 minus 2 is 0. So this value, and add the profit of ith item. So ith item profit is 4. So just add 4 with 0 and take the maximum of the 2. So we get 4 value here. Same way we continue. Here the 2 possibilities are this or from here, and add the profit which is 4. So continue like this. It is very simple. Just all will have identical values. I have given 2 examples. So first row number I we have covered. Next we proceed to row number 2. Again same idea. Row number 2 we consider its weight is 2. So 0 for weight 0 and 1, simply copy from the previous row. Just copy it here. So here we copy it like this. Here also just copy 0 we get. For next again it is very similar. The 2 possibilities are either just from the previous row or the diagonal adjusted by this its weight 2, and add the current profit is also 4. So add 4 to it. So either maximum of 4 plus 0 or 4, you can take either. So its value will be 4. Same way we continue, take this or 4 plus this max. So we get 4. Here also 4 or 4 plus 4. So max is this 8. Here also, so I will just write the values 8 and here also 8. So row number 2 is also completed. Same way we proceed the last row. Row number 3. So row number 3 we see its weight is 3. So 0 1 2 we just copy from below. 0 1 2 just copy 0 0 4. Now its weight is 3. So just below, and its profit is 6. So add 6 from here. 6 plus 0 or 4. take its maximum, we get 4, 6. Same thing here. Either we take 8 or 6 plus 0, maximum is 8. 8 we write. Then 8 or 1, 2, 3. 6 plus 4 is 10. 10 and 8, maximum is 10. Then last value again very similar. Or this. Take the max, 10 we get. So optimal solution we are getting as 10. And how to choose the item? Again, it is very simple. Just follow the optimal path. Which path we are taking? So the path taken is this. And then here, which path we take? We take this path. So taking this path means we are taking this item number 3. Taking this path, again it means we are taking item number 2. And here we are not taking. So the optimal solution is choose 2 and 3. Choose 2 and 3. Weight we get is 5. It fits in the knapsack. Profit we get is 10. And time complexity you can easily compute is big O of n times capital W. So this is called pseudo polynomial time algorithm. Pseudo polynomial time algorithm because it is polynomial in values. It is polynomial in value, not the size. If you take the input size, it will be exponential. So it is pseudo polynomial time algorithm, but actually it is exponential in input size.